asking for less. I don't want the detail. Just what is it? Is it a tomato? Is it a circle?
A line.
It's a line. Okay. Now, if I were to extend the world into 3 dimensions, does anyone know what this is? The equation of in 3 dimensions?
Sphere? Sphere?
It's not a sphere, but since you mentioned that, that's a circle. That would be a sphere, of radius 1. No one's ready to this. Okay. Well, picture's worth 1,000 words. So let me pick some points on here. There'd be 1, 0, 0. And this is the y, this is the x, this is the z. This would be 0, 1, 0. Down here would be 0, 0, 1. And actually all the points on the lines connecting these, well, it's not a triangle, this is just, it's making a triangle as it crosses the 3 planes. It's just a plane. So, okay. But what if I just wanted a line, some line in 3 dimensions? What would the equation of a line be? And it turns out we don't know how to do that yet. There's no equation like this that you can just write that will give you a line in 3 dimensions, or 4 or 5. There's something special about 2 dimensions that lets us do this. So we have to look at something called a parametric equation. In 2 dimensions, a parametric equation might look like this. Say x equals, some function of some variable, say t, y is some function of some t. And so if we want to get points on this curve, we just take some t and we get an x and a y. And then we can run through all the t's in the domain of this function, which might be all real numbers. So what would that look like for this? That's a good question. I didn't go through this. I didn't write this down, but I did do this for another line. So I guess I'll start from there. So I'm going to take a line which goes through these points 1, 2, and 2, 1. And this will demonstrate this better. Okay, so well, let's first look at what the equation of this is. We can use the point slope version. So that would be, say, y minus 2 equals the slope, which we'll get to, times x minus 1. And what's the slope? Well, delta y over delta x would be 2 minus 1 over 1 minus 2 equals minus 1. All right, y equals negative x plus 1, no, plus 3. So here we have the y-intercept, and of course, you can kind of see this as a negative slope. That's just going to be 1. But there's another way to think about this. And now we're going to come back to our discussion on Tuesday of vectors. We're going to think of this is a vector going from the origin to the first point. And then we have a vector connecting this point and this point. And we can take this vector, I guess we'll call it v for the moment, and we can multiply it by some t, could be positive or negative, and we're going to get all the points on this line. So I guess let's give these some letters. We'll call this p, this coordinate, this q, and we're going to say, all right, our line can be described as a vector function of t. It's going to be p plus t times q. All right, let's fill in some of the gaps here. P, that's 1, 2. And what's q? Well, we have the head and the tail of q, but we need to kind of move it over here. So we can, just use the, forgotten the term, the position vector. Okay, so how do we do that? We're going to subtract what? We're going to subtract 2, 1 from this point. I'm sorry, we're going to subtract 1, 2 from this point to move its tail over here. So we're going to subtract what? 2 minus 1 is 1, and 1 minus 2 is minus 1. So we wanted to get back here, so let's write this out. So our x is going to be 1 plus t, and our y is going to be equal to 2 minus t. I'm going to go over that slowly. This is x, right? So x plus t times 1. Y is 2 plus t times minus 1. Okay. So now we have a parametric equation for this line. Let's just be a little skeptical. Can we recombine these to get back to whatever our equation was? Well, let's just add these two equations. The t drops out, and if I solve for y, I get negative x plus 3. So they're the same, except, now we have a different form of this equation. Okay, so what was the point of all that? All right, we have another way, seems a little more complicated, way to describe a line in 2 dimensions. You can do it with just x and y, or you can do it as a parametric equation. we could do the same thing in 3 dimensions. We could have a vector P. We'll give it some coordinates here. Let's say, make it easy, 1, 1, 1. And we could have a vector here, Q, -4, 3, 2 is this way and out in front of the board along Z. So now our line in 3D becomes P plus T times Q. All right, let's see what that turns out to be. Again, we have to move the Q vector kind of out here. We have to move it to the origin. So it's going to be -4 minus 1 minus 5. 3 minus 1 is 2, and 2 minus 1 is 1. And from this, we can extract our parametric equations. So x will be 1 plus -5t, y will be 1 plus 2t, and z equals 1 plus t. It's kind of nice because this works for 2 dimensions or 3 dimensions. Or if we were to deal with something in a higher dimension, we could do it the same way. It's not limited. I guess there's kind of one question I have about floating in my head about all this. I said there seemed to be something special about 2 dimensions that we can do this. It's not so much that it's not that drawing a line in 2 dimensions is special. It's that if you have 2 dimensions, a line is 1 dimension. It's 1 less. That's x plus y equals 1. But if you're dealing with 3 dimensions, we saw this is a plane. So we have 3 dimensions, but this is 2 dimensions. It's 1 less. So you might think, well, it's hard to draw. I don't really know how to draw x, y, z. There's w dimension. In 4 dimensions, if I had an equation x plus y plus z plus w, what would that be? Well, that would be a 3-dimensional space, just 1 less than 4 dimensions. So what's special about just x and y in 2 dimensions is that it's just 1 less than 2 dimensions. A line was. Okay, this is just kind of a topic that I thought I'd throw in because I thought it's interesting, and we can do this with vectors now. Now we know a little bit about vectors. Are there any questions about this? It will not be on the exam, but in your future studies of math, they come in handy. I guess I want to say one more thing. You might think, well, wait a minute. All right, mathematicians, you're you know, you want 4 or 5 or n dimensions. What's the deal there? There's no such thing. There's no such thing as 4-dimensional space, except, you know, Star Trek or, you know, some sci-fi kind of thing. But if, for example, you were studying economics, you might have a model for, say, the economy. And there are lots of different variables in the economy. Not being an economist, I'm not going to embarrass myself and try to give a good explanation, but you might have a model with a lot of different variables, and it conceptually is in some multi-dimensional space. You can't draw it, you can kind of draw a slice through it, you know, the way we, you know, when we draw, you know, a 2D graph, it's really a slice kind of through 3D space. It's on the blackboard. But you don't actually, it doesn't have to be kind of a pure math thing for this to come up in the real world. I'm sure it comes up in physics. Certainly. All right. Okay, so we were talking about vectors, and we saw that there are a bunch of things you can do with vectors. You can add 2 vectors, call them V and U. You can multiply a vector by a constant. You can distribute a constant over the sum of vectors. You can distribute the sum of constants over a vector. It has a lot of similar properties to numbers. There's a 0 vector. You can add to any other vector and get the vector back. There's an inverse to every vector whose sum gives you the 0 vector. Yeah, that's very similar to numbers. The obvious question is, can you multiply vectors? What would that even mean? It's not clear. It turns out that there actually are 2 different ways that we can multiply vectors. One of them we're going to look at. It's called the dot product. And the result of multiplying 2 vectors with the dot product is a number, not a vector. The other type of, this is called the dot product. And we usually signify it with a nice circular dot. The other method is called, cross product. And I'm not sure if we're going to say anything about this. The result of the cross product of 2 vectors is another vector. Cross products in particular, I guess for our purposes, only exist in 3 dimensions. They don't exist in 2 dimensions, and there's kind of a definition you can extend it, but it's different into 4 or higher dimensions. These are really important in physics. If you're a physics major, maybe we'll get to it a little bit. Maybe you've seen it before. But mainly, I want to talk about the dot product. And I'm going to do things a little in reverse from my intuition here. I'm just going to give you some formulas for the dot product that are going to come in handy, and then we'll take a look at why these formulas work. So the first formula kind of looks like this. If I have some vector x1, y1, some v and u, x2, y2, this is the position form. This would be a vector, of course, goes to x1, y1 from the origin, and x2, y2. The dot product of v dot u is just the number x1, x2 plus y1, y2. There's some immediate consequences here, which is you can see because multiplication is commutative, the dot product is going to be commutative. U dot v and v dot u are the same thing. There's some other properties that you can figure out from this definition pretty easily. U plus v dot w, some third vector. Well, you can distribute. This is u dot w plus v dot w. If you take a look at u dot u, in other words, any vector dotted with itself, that's going to be x1 squared plus y1 squared. Which, if we write it this way, the square root of x1 squared plus y1 squared, well, this is what we call the norm of the vector. So this just becomes the norm squared. And that's true for all vectors. Okay, so this is one definition. I have another definition, which, as I said, we're going to develop. Seems to come out of the blue from somewhere. U dot v is the norm of u times the norm of v times the cosine of theta, where you have some u, some v, and the angle between them. Now, it turns out that having both these definitions is really useful. Let's give an example. If I have two vectors, u and v, u equal 5, v equals 2, -8. And I want to ask the question, well, what's the angle between these two vectors? This becomes pretty simple. First, we use this definition. That tells us u dot v is 3 times 2 plus 5 times -8. So that's 6 plus -40 is -36. But I have this other equation which tells us that u dot v is the norm of u times the norm of v times the cosine of the angle. So this is equal to -36. So now we need to find the norm of u and the norm of v. So this is the square root of 9 plus 25. This is the square root of 4 plus 64. So the cosine of theta is -36 over the square root of 24 times square root of 68. So all I need to do to find theta is to find the inverse cosine. All right, well, that's a calculator problem, so give that a shot. Oh. Gotta turn it on. Inverse cosine -36 divided by square root 24 square root 68. And I get error domain. Hate that. Where did I go wrong? Anyone see my error? 3 times 2, 8. Oh. Sorry, -34. Divided by square root of 24, square root of 68. Still wrong.
9 plus, is that 9 plus 25?
I don't
The
know.
square root of 9 plus 25? Because you said it's the square root of 24, which is...
Thank you. You know, you get to this point, you're a professor, you can do like advanced algebra, but you can't do simple math. There's only so much room in your head. Minus, wait a minute. Didn't I say this is -34? That seems like too much of a coincidence. 6 minus 40 and 34, that's right. And you were saying non-square 34. And did I get? Plus 4, yeah, all right. One more try. 34 divided by square root 24, square root 68. No, 34. Still wrong. 6, -40, -34.
Hey, I have an answer.
You did, what did you get?
I got 136.8. 136.8.
Degrees.
Yeah. Did you do radians or did you do degrees? Because,
Well, I was gonna do it in radians, but it doesn't matter.
oh, I did in degrees.
Degrees are fine. We can always convert. Nobody knows where I made a mistake here, huh? But Esther got it right, so 64 plus 4 square is 68. 25 plus 9 square is 34.
Are you doing the inverse of?
Oh, wait a minute. Hold on. This comes from over here, doesn't it?
No, but you said
It's
you said
34,
negative
it's negative 34.
You said it was negative 34
Oh.
because of we.
Oh, okay, all right.
So it would be.
So, is this the problem you did?
Yeah.
Inverse cosine of this? Wow, okay. Negative 34 divided by square root of 24 divided by square root of 68 is 0.81. So why didn't I get a inverse cosine of answer? Oh, I get 2.571. That's radians, I guess. All right. So this is handy. But all right. Yeah, that's what I got on here. Okay. Let's do a simpler one. Same idea. How about the vectors 2, 1, and negative 1, 2? Okay, so let's use this definition. It's negative 2 plus 2. Oh, that's 0. So the cosine of theta equals the dot product times cosine of theta is equal to 0. Oh, so these don't matter. So if the cosine of theta is 0, what's theta? The cosine is 0, that's the x. What's the angle? Pi over 2, or 90 degrees, or as we sometimes say, perpendicular. Well, that's nice to know. If the dot product of two vectors is 0, they're perpendicular, right? If u is perpendicular to v, and u dot v is equal to 0. And likewise, if u dot v is 0, the vectors are perpendicular. Because we sometimes we use dot products with things that are vectors, but they're not kind of pointing arrow vectors. But we still maintain this, this kind of relationship. We have a new name for perpendicular. We use the word orthogonal. Orthogonal, if you've got pointy vectors, it's just they're perpendicular. There are other kinds of vectors that can be orthogonal, but there's no angle between them. But their dot products are 0. So that's nice. Okay, we're going to take a break for a few minutes. And then we'll come back and see how these two formulas, why they're the same, even though they look very different. I'm going to just ask now, is there anyone who wants to come visit me during office hours today? Okay. Okay, try not to make this too painful, but it's good stuff. We saw that u dot v is just, we're going to define the dot product that way, so that u dot u is x1 squared plus y1 squared for squared or the norm of u squared. And what we're going to do with that, we're going to create an example diagram here where we have v and u. And of course, the sum of these is going to be this vector, v plus u, but their difference, u dot v, can be this vector, the other diagonal of the parallelogram. And we're going to make this angle theta, the angle between them. And we're going to apply our law of cosines, which you'll remember is c squared equals a squared plus b squared minus 2ab cosine theta. We're going to apply this here. This side of the triangle is going to be our a, and this is going to be our b, and this is going to be our c. Well, what's the length of c? That's the norm of u minus v squared. A squared is going to be the norm of v squared, and b is going to be the norm of u squared, minus 2 times the norm of u norm of v cosine theta. Oh, that's a mouthful. So this is just the law of cosines is applied to this diagram using these vectors. But before we look at the right side of this equation, we want to look at the left side and expand it. We saw that the norm of u squared is just u dot v. I'm sorry, we saw that, is that right? I've gotten something mixed up here, hold on.
The norm of u squared is just u, like u times.
The norm of u is square root of,
I don't think it's u times v, I think it's just u times u.
I'm sorry, this is the norm of u dot u,
Yeah.
right? Ah, okay, now I know where I'm going. So this fellow, the norm of u minus v squared, is just u dot v. I'm sorry, u minus v, we have over there, dot u minus v. This is now the left side of that equation. So now we're going to distribute using FOIL. So we have u dot u plus minus u dot v plus minus u dot v plus v dot v. Okay, so this is minus 2 times u dot v plus, well, u dot u is the norm of u squared, and v dot v is the norm of v squared. So this is the left side of that equation. So I'm going to write the right side down here. It's the norm of v squared plus the norm of u squared minus 2 times the norm of u, norm of v, cosine theta. So what do we do now? You see we've got the norm of v on both sides, norm of u on both sides. Now we can divide. I guess we're going to divide by minus 2 times the norm of u, norm of v. So that's going to give us the cosine theta is equal to u dot v over norm of u, norm of v. I guess I ran right past where I wanted to be. That tells us that u dot v is the norm of u, norm of v, cosine theta. That's what we wanted to show. So now we have this other version of the dot product that we can use. All right. that's the big stuff for today. Almost all the big stuff. That alone would make the dot product a useful item. However, there's a little more. There's a little more we can do with this. I want to introduce this as just take a look at some vector. I don't know. We'll call it 3, 2. And I'm going to remind you, we have two predefined vectors we call I and j, which are defined as 1, 0, and 0, 1. So I want to take a look at what b dot I is and b dot j. Well, using our first definition, it's just going to be 3 times 1 plus 2 times 0. That's going to be I, dot I. And dot j is just going to be 3 times 0 plus 2 times 1 is 2. Well, that tells us that since v is 3 times I plus 2 times j, that we could write v as 3 times the dot product of v times v dot I. I'm sorry. It is v dot I times I plus v dot j times j. In other words, we can take a vector and decompose it into the sum, a linear combination of I and j, some number times I and some number times j by using the dot product in this manner. That sounds real convenient. We have some vector, we want to know what its components are. We want to know what these numbers are, and we can extract them this way. But this is actually a little more general than I'm describing here. This doesn't just work with I and j. So, to see this, we have to introduce a new idea here. Called a projection. So the idea is we have some vector v and some vector u, and we want to drop from v a perpendicular to u, and we want to create a new vector which we're going to call VP, or V projection, which is going to have the direction of u with the length of, this segment where the altitude dropped to. So it should be pretty clear by now with your background in trigonometry that the length of VP is going to be, or the norm, it's going to be the norm of V times cosine of theta. Just let that sink in for a second. Adjacent over the hypotenuse is the cosine, so, is that right? Yeah. Okay. So now we want to kind of pull a trick here. We're going to invent a new vector we're going to call unit. Remember, a unit vector is a vector whose norm is 1. And we're going to create it by taking u vector and dividing it by the norm of u. Again, this is something we can do with any vector. We can find a unit vector in the same direction as that vector, this way. So now we can take our projected vector, VP, and we can describe it. Here's its length. And we're going to multiply it by this unit vector. And that gives us this vector here. Rewrite this over here because we're going to do something tricky with this. Yes, I can erase this too. So we're going to look back at the fact that v dot u is equal to the norm of v, norm of u, cosine theta. I'm going to divide both sides by the norm of u squared. Not sure if I can pull this together. Let me try. Well, obviously we can move this. I'm going to try and draw this These are the same thing. So I'm kind of lost here in my own crazy stuff, but so VP is this, V dot U over norm U squared times U from over here. And let me rewrite this way. This is our U unit vector. No, I don't really want to do that. I want to leave that here. Okay, so this is what I'm looking for. I have a way of calculating this projected vector now. It's v dot u over the norm of u squared times the vector u. Well, I'm kind of missing the point of all this. It can be kind of obvious to connect these two. If I substitute for VP, yeah. If I substitute for VP here, the projection not onto some U, but onto I of J, what do I get? V onto I is V dot I, but the norm of I is 1, and the same thing with V sub J is the dot product of V and J. So the point of all this is, you know, we can extract the components, you know, perpendicular components this way for I and J. We can do the same thing with any general set of vectors. We just need this additional constant. We have to divide by the norm of u squared. I guess we should do a problem. That might help. Let's take u equals 1 to 4 and v equals -2, 1. And let's look at the vector u projected onto v. So that's going to be u dot v over the norm of u squared times the vector v. Okay, u dot v we can calculate 1 times -2 plus 4 times 1, that's 2, over the norm of u, well that's square root of 5 squared, times the vector v. So that's just -4/5 and 2/5. So So that's how you would use this formula. All right. So vectors, dot products, projections. I want to say something before we go, just a little, since you might run into it, about the cross product. I mentioned that the cross product is a multiplication of two vectors where you get a vector. And as I mentioned, it only works in 3D. And I'll show you why in just a second. So if you have two vectors in 3D, and you want to generate the cross product, this is going to have two properties. One of them is that u cross v is going to be perpendicular to u, and it's going to be perpendicular to v. So again, you have to kind of think in 3 dimensions. If I have two vectors on the board, it's going to be a vector sticking straight out. In addition, it has a formula, the norm of u cross v is going to be equal to the norm of u times the norm of v times the sine of theta, where theta is the angle between them. So as long as theta is some positive angle, this norm has some positive value. But if you had two vectors that are parallel, the cross product would be 0. It would be the 0 vector, and it wouldn't have a direction. So this is one way to calculate the cross product. If instead you have the components, we call them A1, E1, C1, and A2, E2, C2, you can calculate the cross product from these components. It's a little bit tricky, to say the least. There's a formula. I'm gonna try and describe it very briefly. I hope some of you are, well, let's back up. You have a matrix. We have an operation you can do on matrices called determinant. And the way you calculate it for a 2x2 matrix is you multiply members on the diagonal, and then you subtract the numbers on the other diagonal. So the determinant here is 1 minus 6 is minus 5. Now, when you go to a 3 by 3 matrix, such as this one, well, we're going to use different letters here, A2, A3, B1, B2, B3. It's somewhat trickier. There are two ways to calculate this, but the more straightforward way is what we call expanding minors. All right, so I'm going to first look at I, and I'm going to ignore things along the diagonal I, and then have the determinant A2, A3, B2, B3 times I. And then you have to alternate these. So I'm going to subtract, and now I'm going to find what we call the minor of J. Needless to say, this won't be on the exam, right? A1, A3, B1, B3 times J, and then plus the minor of K here, which is A1, A2, B1, B2 times K. Now we just have to expand these determinants. So we get A2, B3 minus B2, A3 times I, minus A1, B3 minus B1, A3 times J, plus A1, B2 minus B1, A2 times K. And, you know, here you have the three components of your vector for the cross product. Now, I think that's where we're gonna round up for now. I want to ask, does anyone here have a bicycle? A bicycle where the front wheel comes off easily, quick release? Okay. So here's something you can try if you haven't already. You take your bicycle wheel, and you hold it on the axle, right? You spin it, and then if you let go of one side, it won't fall over, right? But it will turn, right? So what's happening here is your wheel is turning, and we use this model of a vector, which is now along the axis. So just because something's turning, that's the way the vector goes. But you also have another vector pulling down the force of gravity. And if you take the cross product of these two vectors, that tells you which way the bicycle is going to spin around instead of falling over. So application for the cross product. All right, before we go, Tuesday will be review. Please take a look at the review sheet. You know, take a look at the, you know, I posted this. Take a look at some of the problems I posted, example problems. Take a look at the cover sheet for the exam, which is going to give you some information you'll have during the exam. Bring in any questions, any old homework questions you have. Questions about, you know, life, the universe, everything you need to. And we'll spend next Tuesday going over anything we've done in the class in preparation for the exam. And thank you.